Great. So, hello and welcome to the fifth PMRF TA lecture on this course, Phase Equilibria in Materials. So, this week we have seen that the different type of microstructures, both equilibrium and non-equilibrium conditions formed under both the conditions, and then we have seen a few of the most popular phase diagrams that are available for binary systems. Okay, so we'll just go through what we have covered in this week. Right. So, okay, so we have seen the equilibrium microstructures forming for a binary eutectic system under equilibrium cooling. So let me just draw those. Okay, so this is a, let's say, lead tin system. So we have lead here, and we have weight percentage of tin increasing this way, and we have the solvus lines in this manner. So I'm only drawing the lead rich region of the phase diagram. It's because we will be seeing with the gradually increasing concentrations how the microstructure will evolve. Supposing we are somewhere within the solvus region. So, assuming somewhere here, and this is a liquid phase, and let's say if we have alpha solid solution, we have the alpha plus liquid phase here, and we have alpha plus beta here. Okay. So we have seen that as you go on cooling this from this composition, which is rich in lead, starting from the temperatures where it's completely in liquid, so we'll be having 100% liquid here, and as we go on crossing the liquidus, so we'll have a region here wherein we will be having certain precipitation of alpha, so we'll have alpha plus liquid here in this portion, and then as you go on further cooling and crossing the solidus, so we'll be having completely alloy of alpha. So this is 100% alpha. Okay. So just quickly see how the microstructures look like for 100% liquid. Of course, like maybe I'll just draw ellipsis. So at point let's say 1 and 0.2. So this is 0.2 and this is 0.3. So at 0.1 we'll be having liquid of composition, let's say this is C0. So we'll be having 100% liquid of composition C0. And at 0.2 we'll be having certain precipitation of the alpha phase. So this is alpha and this is liquid, still in the liquid part of the phase diagram. So alpha and liquid will be in equilibrium. So herein the compositions of the liquid will be given by the point of intersection, and we know with the liquidus and solid will be with solidus. So alpha composition here is less than the composition of the melt that we have taken initially, because now here it is the liquid has taken some of the alpha, right? So the liquid is rich in alpha. So Cl is greater than C0. Okay, and upon further cooling at 0.3 we have 100% alpha. 100% alpha of composition C0, because here there is no liquid coexisting with alpha here. So we have grains. So by this lines I mean to refer the orientation of grains, not the lamella. So wherever we mean lamellas by these lines, I'll be specifying it separately. So that those lamellas are generally formed when you have a prolithic deposition. So this is alpha and this is of composition C0. This is 100% alpha. Okay. So we have seen this. Now what happens if we just go somewhere inside this boundary, right? And then we cross this alpha plus liquid phase, and then we cross alpha, and then we go on crossing this alpha plus beta phase. So we'll quickly revise that part. So what I'll do is I'll just to save time, just copy paste it here. Okay, so here so this was a C what we have taken initially. Now we'll be taking composition somewhere lying here. Okay, let's say this is C1 weight percentile. So here, if you are starting at a temperature above the liquidus, we'll be having 100% liquid here, and the liquid composition will be uniform, equal to C1. And as you go on cooling, so let us mark our points. Let's say, rather let us take this as C2. C1, this point A, this point C, and this is point B. So we'll quickly see how the microstructures will look like. So at point 1 we have 100% liquid, point A rather. So we'll be having 100% liquid of field composition C1. So it is liquid of composition C1. And then as we go on crossing this liquidus, we'll be having precipitates of alpha forming. So at point B, so we'll be having different crystallites of alpha forming at random orientations. So these are the pro-eutectic alpha, by the way, because they are forming above the eutectic temperature. We have not crossed it yet. So we have a liquid of composition greater than C1, and we have alpha, pro-eutectoid alpha of composition lower than C1. And as we go on crossing the solidus at point C, we have a complete precipitation from the liquid. So we'll be having 100% alpha here. So again, these are the different orientations of the alpha grains that are formed. So whatever crystallites that are forming in liquid phase, they will keep on growing, and ultimately they will reach to a terminal limit where the sizes are coinciding, the different orientations are coinciding, the grain and those are the ones that we call as the grains. So these are different grains of alpha, and this composition of alpha is equal to C1 itself. And as we go on crossing this solvus boundary, an interesting thing happens, because now that we have complete solid thing here, so we have a solid to solid phase precipitation. So there is no liquid here, by the way, and let's say if our microstructure is something like this as earlier. Something like this. So what will happen is, now we have some small crystallites of beta forming here as well. So how these crystallites will look like? They will rather look like really small flakes with like high aspect ratio, something like this. And these are formed within the alpha phase itself. So these are the beta phase, and the composition of beta can be again given by, if we draw just a tie line from here. So the part where it touches the other solvus towards the tin-rich region, we have that will be the composition of the beta, and the alpha composition here is lower than the, because it is expected, because now that we are precipitating out something from the 100% pure alpha, which was of C1 composition. So we'll be having alpha which is leaner in tin, right? So that's the reason why we have alpha phase here. This composition is lower than C1. Okay, and you can see it all because the point it touches the curve. This will be the composition of alpha. Alright. So third case, if you are completely in this region, what will be the case? How will the crystallite look like? So quickly drawing the graph again. So now that we have bordered somewhere far away from the dead rich part, so we have in those regions, right? So this liquid, this is alpha plus liquid, this is alpha, and this is alpha plus beta. This is temperature, and here is the eutectic temperature, right, TE, and we are taking a composition somewhere here. So we take a temperature which is higher than the liquidus temperature here for this composition, and then we gradually go on here B, let's say C, just above the eutectic we have taken C, and just below the eutectic we have taken B. Okay, and this is the eutectic composition CE, and this is the C maximum of alpha that can be accommodated at eutectic temperature. Okay. So to draw that, we again need to have the phase windows. Okay, so let's start again with point A. So we'll be having 100%, and this is the composition, let's say C2, and this will be completely liquid molten state. So it is liquid of composition C2. Okay. And then we go on cooling it. So at point B we'll be having certain small crystallites of alpha forming. Those are very small though, because we have just started to precipitate it out, and the remaining parts will be the liquid. So this is liquid of course composition is greater than Cl is greater than C2. You can see if I draw a tie line like this, the point where tie line touches the liquidus will be the liquid composition, which is higher than C2. The point where my tie line touches the solvus boundary here will give me the composition of alpha. So C alpha, these are the alpha crystallites whose composition is greater than C2. Okay. And at point C, which is just above eutectic temperature, infinitesimally above eutectic temperature, we'll be having very large grains, because the same crystallites that we had started precipitating out, they will act as seed or seed crystals, and these same crystals will keep on growing, and they will grow, and 100% of growth will be achieved as we cross the eutectic temperature, and then we have 100% solid. So we have alpha here, whose composition is just close to C alpha E, and we have liquid here, and the remaining part is liquid, and liquid of composition just close to CE. Okay, now that we know this, so it's easy to guess what comes ahead. So at just below the eutectic temperature, we'll be having so whatever the alpha will be there, it will still remain as alpha, and we call it as pro-eutectic alpha, because these alpha were formed before the eutectic temperature. So these are the pro-eutectic alpha in the microstructure window, right? And what else we'll be having is lamellas. And what I mean by lamella is basically a layer by layer structure, something like this. Right. So assuming this is the beta phase here, let's say if this is beta, of course my in the eutectic mixture I also have alpha here, so I'll draw alpha but with maybe a darker shade of red. So this part, my folder part is named alpha, and this is eutectic alpha. And the bright red was my pro eutectic or primary alpha. So you can call it pro eutectic or primary alpha, right? And this is how the microstructure will look like for hypo. So this is all the regions that we covered were hypoeutectic, and hypo and hyper are used with respect to the composition. So here all the composition that we had spanned yet are all lower than CE, right? C less than CE. So this is the reason why it's called as hypo. So hypo is low, hyper is high. So low eutectic means lower than eutectic composition. So hypoeutectic region. Okay. So now what happens if we are just at the eutectic point, and that is the last we'll consider, because after that after that it's very easy to do the same thing for hypereutectic thing, just that the alpha will be replaced by a more beta rich phases, right? So we did two of the phase period here because, as you can see, we have only two regions of interest in this part. Okay, so we'll draw the same again. So this is the percentage of 10 by the way, this way. So this is my TE. So what if I take a composition C3, which is equal to my eutectic composition CE. Okay. So at point A and point B, because we don't cross any phase field, so we just need 2 points to explain the whole cooling process. At point A, of course, since we have 100% liquid of composition, homogeneous composition equal to Cl is equal to C E, the eutectic composition, right? And as we cross upon cooling, so what will happen is at point B, we will be having very nice layered precipitates. Completely layered or laminar structures, and following the same convention that we had mentioned, like beta will represent with blue, so this is beta, and we have alpha, so we have alpha like this. So we have an alternating layers of, or rather we call it as lamellas of alpha and beta, and this is what we call as the eutectic mixture. Right, and we don't have any excess pro eutectic alpha, because the reason is because we are directly converting liquid to the alpha plus beta phase at the eutectic point. So yeah, and if we just take a close look, what we'll be having is like a very layered structure of alpha and beta lying close together parallelly, and that is how the precipitation happens at the eutectic point. So we'll quickly go through an example of what we have also covered this week, that is the non-equilibrium cooling. So what happens in non-equilibrium cooling, we have seen is that if we are cooling liquid fast enough. So let's briefly describe non-equilibrium cooling. So if you are cooling, let's say, a melt fast enough such that the diffusion reactions are not they don't follow the rate of your cooling, so the solid-solid diffusion will be a barrier then. So instead of thermodynamic barrier, now we have kinetic barriers preventing the homogenization of the phases, and that's the reason why we'll have segregation, or rather we have a heterogeneous phase or core microstructure formation. Okay, so we'll see a very easy example of it. Okay, let's say we have a binary isomorphous system, and we already know binary isomorphous, we have like a completely miscible solid solution. You can assume it as like a copper or nickel, and we have a solution at this point. If I draw a line vertical, let's say composition X. Okay, and if I just we already know that it's liquid, and it will be, let's say, an alpha plus liquid, and this is completely miscible solid solution alpha. And under perfect equilibrium, if you are cooling it slow enough, we will be just following the same phases that we cross it in the phase diagram. So as we cross this liquidus, we'll have solid solution, solid precipitation, and as we cross the solidus, we'll be having complete solid below that, right? But what happens is, like, if you are cooling it a bit fast, so let's say we are just at the point of precipitation, so we'll be having liquid of composition X and alpha of composition, let's say this one, alpha 1, right? And this is alpha 1, and let's say this is temperature T1, and this is L1. So if you are cooling it even lower, we should be having L2, and we should be having alpha 2 at T2. So T3 and T4 likewise. L3, alpha 3 at T3, and let's say T4 is here. So this is L4, and this is all equal to Cx. So, that is equal to this X composition. So what will happen is, if you are cooling it under non-equilibrium conditions, so the overall composition, let's say from if you go from T1 to T2, the composition of alpha changes from alpha 1 to alpha 2. So from T1 to T2, as we go, I change my alpha 1 composition to alpha 2, and for alpha 2, because we see alpha 2 is reaching B, because it is right side towards the percentage of B. So it is richer in B. So B atoms will diffuse into the existing crystals, and A atoms, on the other hand, will diffuse out. To accomplish this, the change in composition. Similarly, the liquid composition, as you go from T1 to T2, will change from L1 to L2. The final solidification happens here at about T4. The last melt will solidify to have the composition L4. The last liquid will have the composition L4, and the last crystallites in this phase field will have a composition of alpha 4. Right? So if the melt is cooled too quickly for the equilibrium conditions to be maintained, the crystalline and liquid phases will develop some composition gradients. But because that diffusion, as we know, the diffusion in liquids is higher than diffusion in solids. That's the reason why we don't see immiscibility in liquid. So we have a completely homogeneous liquid, but rather solid will be what is we'll see that they will be heterogeneous in composition. So homogeneous liquids. That's the reason why we have homogeneous liquid phases, but not solids, right? So if we just visualize the phase, I'll not draw the microstructures, but if we just visualize it, as we cool it down, so the alpha crystals will start growing. However, the composition of the alpha crystals that are precipitating out will vary at each and every point as we cool down. Okay, so ultimately starting from alpha 1 and ultimately ending with alpha 4, which is very, very different. So alpha 4 is much higher in B as compared to alpha 1, which is much linear in B. Okay. So the average composition is of the whole liquid phase, you know, it's going to be much different than the equilibrium conditions. So what will happen is, so as you cool down, and draw the next slide. So let's say initially we have crystal of alpha 1, so what will happen is, so the same crystal of alpha 1 composition now will be surrounded by another crystal of alpha 2 composition. So this is alpha 1 and this is alpha 2, and to accomplish that, some of the B atoms will need to go in, some of the A atoms will need to go out. Okay. Similarly, like if I go on cooling it, because of the diffusion barrier, we have alpha 1 here. Again, we'll be having a core of alpha 2 surrounding it, and at the very end, which is we'll have the crystals which are very recently formed, but the compositions are much different than the earlier precipitated crystals. Let's see, this is alpha 3. Okay, and again to accomplish that, we need some diffusion of B inside and some diffusion of A outside, because we are getting richer in B and linear in A. Right, and finally we'll be having a very, towards the very end, we have a very core microstructure something of this sort, right? And let's say this, the whole outer one is alpha 4, and again this will keep on happening. This P diffusion of P, inward diffusion of P and outward diffusion of A will keep on happening until we completely solidify it, right? So as long as we have liquids, we'll have this sort of diffusion, and that is happening, and we will have this non-homogeneous phase formation of one after another. So this is during the so A rich. Solid solution. Okay, and so by the way, this composition should have been not over confusion, but I'll give primes. So this is alpha 2 prime. Why is prime? Because we'll see that instead of following this composition, we'll be having certain variation in the composition. So since that we have a higher amount of composition than usual, so the liquid will kind of overshoot here. So if I draw it by so the liquid will kind of liquidus will overshoot like this. Okay. And the solidus will overshoot something like this. Okay, and this is just exaggerated to this point. So this is alpha 1 prime, or rather, yeah, let's keep it prime for alpha 2 prime, alpha 3 prime, alpha 4 prime. Okay, so that's the reason why our solidus will be shifting downwards, right? And because of the non-equilibrium conditions that we have. Okay, so we have covered this part. I think this is covered. So we'll quickly now venture into a few of the numericals that we'll discuss based on these concepts. So give me a minute. Okay. So we have been given a binary eutectic copper silver CuAg phase diagram, and so we have been asked to make phase analysis. So phase analysis to analyze what kind of phase and what are the composition and what are the amounts of phases, all three, right? For an 88 weight percent. So 88 weight percent is somewhere very close here. So we'll draw a line. Near to 88, so which will represent our composition that we are targeting. So 88 will be closer, much closer. So this is 88, somewhere here, right? Fine. And so we have been asked with 88 weight percent. So this is weight percent silver. This is at weight percent. So we have been given in weight percent. So be careful. Draw it in the axis, the bottom x-axis, right? So this is where we are at now, 88%, and at 1000 degrees centigrade. So 1000 degrees centigrade, just draw a diagram. And again, this is centigrade, not in Fahrenheit. So don't draw the line here. Rather draw the line for the centigrade corresponding to the centigrade scale. Okay. So the phase is present at 1000 degree, at 800 degrees. So 800 degrees, let's go ahead and line. 780 plus, so 780 should be the objective. This part 780, so it's just above it, 780 and just below 780. This and this, right? And this is A, this is B. Just here is C and just here is D. Okay, I'm not writing because we don't have much space here. Anyways, so A at 1000 degrees centigrade, the phases present are liquid, right? And composition is 100%. So 100% liquid or composition, 88%, 88% of silver. Sorry, not 100%, 100% liquid of 88% silver. Okay, so this is at point A. At point B, the chemical composition at point B will be alpha and sorry, the beta and liquid here, because we have beta rich phase here. So phases present liquid and beta. What is the composition of liquid here? The composition of liquid can be given by the intersection of the liquidus here. So liquid is a liquidus. And if we just drop a tie line, not tie line, we drop a vertical, it should be somewhere close to 80. So it doesn't look like it, but it is about 78%. Rather, it looks like above 80. So yeah, this is because we are doing it roughly. So nearly 80, you can assume it will be 78% silver. And you can deduct it from 100 to get the percentage of copper, right? And beta, the composition of beta will be given by the intersection with the solidus here. So if you could drop it, it will be much higher than 90 even. Right, about 93%. So this is about 93% each. It's in beta. Okay. So what are the amounts of phases? So the amount of phases can be given by Lever rule. So the percentage of weight percent of liquid can be given by, so this is liquid, so we'll consider this arm, which is arm from liquid, which is 93 minus 88 divided by 93 minus 78 into 100, which gives me approximately 33%. Okay, and amount of beta can be given. Now beta is something which is here, so we consider the arm which is away from beta, so which is 88 minus this. Oops. Yeah. 88 minus 78 divided by 93 minus 78 times 100%. That gives me approximately 66%. Of course, you can take 100 complement of 33, that is 100 minus 83 is approximately 66%. That will also can do it. And okay, so now we have been also asked like to draw the microstructure using this phase fields. So for that, this ellipse again. Or bit a smaller one. Okay, so we already know that we are in the liquid plus beta region, so we'll be having some chunks of beta. Rather, I think we should draw this in blue as per our convention to avoid confusion, because we have been drawing beta in blue, right? So this is my beta phase, and the remaining part is my liquids. Okay, and the composition are given as such. And this beta is known as primary beta. The same concept that we have seen earlier. It's called primary or eutectic beta. Okay. So now we move on to 780 plus T, that is at point C. So at point C we are just above the eutectic point. Infinite 70 above 780. So here what phases we have. So the phases present will be, you can see the phase diagrams and you can directly tell that the phases will be nothing but the beta and liquid, right? We have liquid plus beta. What is the composition? So this liquid of composition, we'll see the intersection of this tie line with the liquidus, which is here. So this is 71.9. So we have a liquid of composition 71.9% silver, and we have beta of composition where it touches the solvers. It touches the solvers here, which is 91.2 given in this diagram. So we have 91.2% of silver composition of beta. Now what are the amounts? So the amounts of phases. So we have seen the phases, the composition, but now let's see the amount value. So which percentage of liquid is given by which arm? Which percent of liquid is given by this arm, which is 91.2 minus 88 divided by the total arm. The total arm is 91.2 minus the eutectic point, 71.9, right? Into 100%. That will give me 16.5% approximately. And weight percentage of beta is 100 minus weight percentage of liquid, that is equal to 88 minus 71.9 divided by 91.2 minus 71 into 100%, should give me 83.5%. Okay. So this is the percentage of beta that we have just above the eutectic temperature. So at point D. So yeah, by the way, I have to draw this phase field also. This is how it will look like. So we have a beta that is precipitating out. So we have beta that is precipitating out, but we have very small amount of liquid as well. So this is beta. So this is my beta, and the remaining part, and this is just about detecting temperature. I have some minor amount of liquid outside. Okay, at point D, which is 780 degree minus delta T, just below the effective temperature, what we'll be having is combination of beta and alpha plus beta. So whatever the beta that we have formed is the detectored or primary beta. Whatever liquid it was, we have in the intervals. So this liquid will be actually forming this alpha plus beta phases. Okay, so this is what it will look like. So we have chunks of B. Similarly, we have chunks of, not chunks but lamellas of alpha phase here. This is alpha, by the way, and this is alpha in alpha plus beta detecting mixture, and the blue lamellas which are sandwiched between the red. Right, these blue lamellas are beta. This beta we have both in the alpha plus beta as well as this beta in alpha plus beta, and we have beta as pro-detecting beta. Okay, and we can do the analysis of the phases that we have. We have alpha and we have beta, and the composition of alpha and beta. This alpha will be of composition, so we just draw a tie line crossing up to this point. The composition of alpha will be 7.98% silver, and composition of beta will be 91.2. This beta will be 91.2% silver. Okay, and accordingly the weight percent we can get by the Lewis rule amount of phases. We can get the weight percentage of alpha, that we can get it by this arm. So the alpha is this part, so we can get it by this arm, so which is 91.2 minus 88 divided by 91.2 minus 7.9. That should be 3.84%. And similarly, the weight percent of beta is 88. So we can see it from the diagram again. Weight percent of beta is this part, which is 88 minus 7.9 divided by the whole arm, that is 91.2 minus 7.9. Okay, so 88 minus 7.9 divided by 91.2 minus 7.9. It should come out to be about 96.16%. Okay, so it's important to note that we have been asked the composition of alpha and beta in terms of the actual in terms of the actual contents of alpha and beta. If we had it been that we were asked that find out the percentage of alpha and beta in terms of alpha and alpha plus beta, what we would have done instead is that we would have rather drawn a perpendicular line from the eutectic point like this, and we would have taken this as alpha plus beta uh, boundary, and the intersection of the tie line with this boundary will give us the composition of alpha plus beta, and of course on the part the lever that is facing away from the alpha plus beta line will give us the amount of the alpha plus beta eutectic mixture. So that's the way of calculating the total weight percent of alpha plus beta, and of course we know the total weight percent of beta, which is in the eutectic pro-eutectic form. So if we deduct the total amount of alpha existing minus the alpha plus beta that is basically forming after the eutectic point. So what we'll be having instead will be the amount of alpha or amount of beta. The other secondary phase that is here is alpha here. So the amount of alpha in the laminar phase you can find out by that. Okay. So maybe I can just write it for noting. Okay, maybe we'll just encounter it in the next question itself. Okay, so we have been given that a 500 gram of 40 weight percent silver and 60 weight percent copper alloys cooled from 1000 degrees centigrade. Okay, so copper and silver, they make a binary eutectic phase diagram. Something like this. So we are somewhere here. Okay, this is 40 weight percent silver, and this is weight percentage of silver increasing this way, which is 100% Pg. Sorry, weight percentage of silver, this is copper. And this is the temperature of the y-axis. We know this is alpha. This is solid silver, alpha plus liquid, beta plus liquid, and alpha plus beta in this phase right here. Okay. So we have been asked how many grams of liquid and pro-eutectic alpha are present at 850 degrees centigrade. So this is 780 degrees centigrade, by the way. Eutectic temperature. Okay, and at 850 degrees centigrade will be so working out this for working this out, we will always be given the actual phase diagram, wherein we can get the compositions from the intersection points, right? So at 850 degrees centigrade for question A, at 850 degrees centigrade, so the weight percent of liquid can be given by this arm, which is 40 minus this was 7.9. Write it yourself. So it can be given by 40 minus 7.9 divided by 52 minus 7.9 times 100%, which gives us about 72.8%. Now weight percentage of pro-eutectic alpha. So let us write pro equals pro alpha, and that will be equal to, so this part is alpha, so this region will take, which is 52 minus 14 divided by 52 minus 7.9 times 100, which gives us approximately 27.2 percentage of pro-eutectic alpha forming before the eutectic point. So the weight fractions, we already know that we have 500 gram of alloy. So the weight of so we have been asked the weight, so to convert this percentage into weight. So weight of liquid phase is 72.8% of 500 grams, which turns out to be 364 grams. Okay. Similarly, the weight of pro alpha, the primary alpha, can be given as 27.2% of 500 gram, which is 136 grams. Okay, this is the answer to this bit. So the second question asks, how many grams of liquid and pro-eutectic alpha are present just above the eutectic point. Okay, so by the way, because this curve is very steep, so this point lie very close to each other, so it's not apparent in this schematic because I have done it freehand way. So but this is also close to 7.9, so you can just imagine it being almost vertical. It's very steep at this point, and this is 71.9, it's already mentioned, 71.9. So you can just get the percentage of liquid, so we can get the weight percentage of liquid by this. I'm not going to do it bit by bit, I'll just guide the readers how to do it. Okay. So the weight percent of liquid will be this green divided by this total blue into 100, and similarly the weight percent of alpha will be the pro-eutectic alpha will be this part divided by the whole line into 100%, and that will give you the comparative weight percentages in percentage basically. So you have to find out, for finding out the actual weights or the absolute weights, you have to multiply it or take the percentage of 500 grams and you will get the amount in grams of liquid and pro-eutectic alpha. So the third question asks, this is an interesting one, like the alpha which is present in the eutectic structure at just below the eutectic point. So just below the eutectic point, we'll be having alpha plus beta structure, and how are we going to find out the alpha that is present in the eutectic structure? So the alpha that is present in the eutectic structure can be given by the difference, basically this, right? So amount of alpha in the eutectic structure can be given by the total amount of alpha. So eutectic structure is lamellar, by the way. So total alpha minus the pro-eutectic alpha. So the total alpha we can get by this part. So we can get the total alpha draw another line of the color, maybe black. Okay, so if I draw a line like this from end to end, right, which is about 91.2 here, from 7.9 to 91.2. So in this case, my tie line is spanning from alpha pure alpha to pure beta, right? And crossing alpha plus beta phase. So to find out the total amount of alpha, we have to take this line, so this part of the tie line divided by the total tie line. So 91.2 minus 40 divided by 91.2 minus 7.9 into 1% will give me the percentage of the alpha, total alpha. Okay. Now from that percentage of total alpha, if I subtract the percentage of alpha existing in the proeutectic as proeutectic alpha, so the total amount of alpha existing as proeutectic alpha we have calculated in the second bit, right? So the total amount of proeutectic alpha is basically this part divided by this whole line, that is the amount existing in this proeutectic alpha, right? And if we subtract it, we'll be getting the alpha that is existing in the lamellas. So the alpha existing in the eutectic lamella structure, we can get by the difference. So similarly, we can get the total amount of beta that is present in the eutectic structure. So total amount of beta which is in the eutectic structure, we can get it by the summation. So rather by the difference, right? Because the microstructure is something like this. So we have proeutectic alpha, and around these regions of proeutectic alpha, we'll have lamellar structures of alpha plus beta. Beta I'm representing in blue, alpha in red. Okay. So this is alpha in alpha plus beta. This is beta in alpha plus beta. And black one is the proeutectic beta, sorry, proeutectic alpha. So the amount of beta which is present in the eutectic structure can be found out by just taking the difference with respect to the total. So beta is basically this part, right? So we take this arm, divide the total arm into 100 is really a percentage of beta in the eutectic structure, and if we just multiply this weight percentage of beta in the eutectic structure with 500 grams, we get the total number of grams which is present in the beta present in the eutectic structure. Right. I hope this should be clear. Now we move on to the next question. Okay. So an alloy of 30 weight percentage of lead and tin is slowly cooled from 250 to 27 degrees centigrade. So we have been asked whether it is hypoeutectic or hypereutectic. So I think lead and tin we have solved it in the last class. I'll just borrow the phase diagram from that. Is this one? So we have a net tin phase diagram here. So we have been given composition about 30 weight percentage of net. So 30 weight percentage of lead is corresponding to 70 weight percent of tin, which is here, right? This is 70 weight percentage of tin, and this is where we are. So you can see that with the composition, so this is C naught is equal to 70 weight percent tin, and this is greater than CE, which is equal to 61.9 weight percent tin. Therefore, we are crossing the eutectic point, so this is a hyper eutectic alloy. Right? This is a hyper eutectic alloy. This composition is lying right. So this composition is lying right to the eutectic point. What is the composition of the first solid to form? So it is cooled from 250 degrees centigrade. Yes. So this is 250 degrees centigrade. And the first solid will be forming as we cross the liquidus here, right? And if we draw a tie line, so the first composition of solid can be given by the intersection of tie line with the solidus, which is this one. Very close to 100% tin, by the way. So C beta at this let's say point A, B, at point B is given by the composition of beta at this point is given by approximately 98 weight percentage of tin, right? And the liquid is given by the almost 70. So Cl here is almost equal to 70 weight percentage of tin. So you can calculate the value different weight fractions of liquid and beta just below this point. Anyways, so the third point is what are the composition and amount of phases that is present at 100 and just infinitesimally above 180 degrees centigrade. So 183 is the eutectic temperature of this system. So just above the eutectic temperature, we have solid of beta, pro-eutectic beta. So the phases are eutectic beta and liquid, and the composition of this beta, pro-eutectic beta, can be given by the intersection this one. So this is basically this part that gives me about 97.5, 97.8. So this is 97.5 weight percent tin, and liquid will be of composition 61.9 weight percent tin, and the amount of phases can be given by the liquid rule. So amount of phases, so percentage liquid can be 97.5 minus 70 divided by 97.5 minus 61.9 200. which gives me 77.2% of liquid, and the weight percentage of beta can be given by, so this is beta, so this arm will be taken, so this is 70 minus 61.9 divided by 87.5 minus 61.9 into the 100%, which is approximately equal to 22.8% amount of weight percentage of beta that is forming just above the effective temperature. And what is the next question asks just below the effective temperature? So question D, just below the effective temperature, it is 780 minus delta T. Oh, sorry, it's 183. I just remember the last example. 183 minus delta T. We'll be having alpha plus beta phases, right? And with alpha plus beta, we'll be transforming from the transforming from the liquid phase, and the beta will be staying as before beta, that was precipitated out, will be staying as pro-eutectic beta. So at 183 minus T, so the composition of the phases are beta and alpha plus beta, right? So if we just take intersection, right? So my composition of alpha will be this one, the composition of beta will be this one, right? And it's about 18%. Okay. So the beta here is of composition of 97.5 8% in. And the composition of alpha is 19.2. The weight percent of total alpha, you can find out by Euler rule. Weight percentage of total alpha can be given by, so this is alpha phase, so this 97.8 minus 97.5 minus 70 divided by 97.5 minus 19.2. So if we take 97.5 minus 70 divided by 97.5 minus 19.2 into 100%, that should give me approximately 35.1%, and weight percent of total beta. Weight percent of total beta can be given by, again, this is the beta phase, so weight percentage is this part, so 70 minus 19.2 divided by 97.5 minus 19.2. That should give me 64.8%, right? This is part D. Part E asks, okay, so the part E is asking what are the amounts of phases at each temperature. So what are the amounts of each phases present at room temperature? So at room temperature we are at about here, so this is 15, so half of that is here. There. So that at room temperature, so as the alloy is cooled below the detected temperature, we have the we can see it from here, right? So as the alloy is cooled below the detected temperature, the tin content in the alpha phase. So the alpha phase is getting leaner in tin, right? So because the solvent is going this way, so my C alpha is going leftwards, that is leaner in tin. So the lead content in beta phase. So the lead content in beta phase, both of them are actually reducing, right? Because as I go down, my tin concentration in beta is increasing, and my lead concentration in beta is also increasing this way. So as the alloy is cooled, below the temperature, tin content in alpha phase the lead content in beta phase. Further reduced. However, at room temperature, it is closer to 20 degrees. We have no equilibrium. No equilibrium attained because we are at such so low temperature that the diffusion rates are minimized. Because of the very slow diffusion, so the concentration will not be able to follow the equilibrium curve, and that's the reason why you can see that this curve, they don't exist below, let's say, 50 degrees centigrade. At about 25 degrees centigrade we have no equilibrium curve part of the equilibrium diagram here. So if we just take an approximation and if we extrapolate this solvus below this below this 50 degree limit that we have right now, so it will approximately, if we just go this way, so this approximately comes out to be about 2%, 2% weight percent of tin. And this approximately goes, if you extrapolate it, it touches the 100 because it's already very close to 100 here. Approximately 100, right, at this 25 degrees centigrade. So weight percentage we can get by an approximation. So the weight percentage of total alpha can be given by 100 because we have approximated it as 100 minus 70, which is my composition right now, divided by 100 minus 2 into 100%. That should give me 30.6%. Similarly, if I just take the complement of it, the weight percentage of beta, the total beta, can be given by, so these are the total. When I say alpha and beta, we are saying total alpha and beta, not in the decomposition also. Total in the total microstructure. So weight percentage of beta can be given by 70 minus 2 divided by 100 minus 2 into 100%. That should give me 69.48%. Okay, so this is what the question had asked us. So moving on, we have been asked to draw a hypothetical phase diagram. So we don't know, because as of now we are taking real life examples like aluminum, silicon, copper nickel, and so on. In this case, we don't know what material it is, but we have been given certain clues to find out which kind of material it is, and to draw the phase diagram of those material, which is hypothetically stated right now. Okay, so we'll see what we have been given us. What have been given to us? So the phase diagram for metal A and B between temperatures of 600 degrees centigrade and 1000 degrees centigrade are given. So first clue is that we have a temperature range here rather than extending from the room temperature like we have seen in the previous example. We have a temperature between 600 to 1000 degrees centigrade, right? And the melting temperature of pure A is given. That is, the melting temperature of pure A is 940 degrees centigrade. The solubility of B in A is negligible, so we won't be having a dimple, right? So let us see. So basically, in this rightmost part of the diagram, which is region A, so instead of having a dimple like this, which represents some solubility of B inside A, we'll be having no dimple. So this phase diagram will start from the pure A, okay? And the melting temperature of pure metal B is given by 830 degrees centigrade. The maximum solubility of A in B, so towards pure B region, like it's given that the maximum amount of A B can tolerate is about 12.8%, right? So we have a dimple of 12.8% A corresponds to about 88.8% B, right? And this is the dimple that will be forming near the B ridge region. Okay, so this is what we know right now, and this occurs at about, and the maximum occurs at the peak at 700 degrees centigrade. Okay, the solubility at 600 degrees centigrade, the solubility of A in B is 8%. So at 600 degrees centigrade, as we lower down the temperature, right? So this reduces to 8%, which corresponds to 92.8% of B, right? So this is 92 right now. So it has increased, as you can also already see in this diagram. And at one eutectic occurs, so we have two eutectic points, I guess, multiple eutectic points. So first eutectic occurs at 700 degrees centigrade. The temperature is the composition is 75.8% B. Second eutectic occurs at 730 degrees centigrade at 68% B, and third eutectic occurs at 755 degrees centigrade at 48% B. And there is a one congruent melting point. Now, congruent melting point refers to the congruency. So, congruent melting point means we have a direct melting. Direct melting means my solid will directly convert to a liquid without any liquid of the same composition. Okay, so solid converts to liquid of the same composition. So yeah, so this is my congruent melting, and this congruent occurs at 780 degrees centigrade. Second congruent melting point we have been given occurs at 755 degrees centigrade. And intermetal compound AB exists, and intermetal compound AB2 exists, and the positions of them are already specified here. So given all these clues, now it's easy to chart all the points that have been already given to us. So if we are trying it, I suggest you to try it on a graph paper so that you can actually get the compositions right. is A, this is B. Okay, so we have been first told that there is a intermediate compound AB, right? AB at 51 weight percent, and if you see that this composition is equal to this composition, which is congruently melting, right? So that tells us that AB is congruently melting. So it gives us a clue that AB is congruently melting. If we have AB here at about 51 weight percent, so this is about 51 weight percent of B, and again 67 weight percent and 33 is like AB2, so we have been given AB2, which is a 67 weight percent. So 67 weight percent is somewhere here. This is AB2 phase, intermediate phase that is forming, right? And as per the clue, we have been given that it is congruently melting in nature. Okay, and to see whether if it is higher or lower, we have to compare the congruently melting points. So it is 755 for AB2 and 780 for AB. That tells us that this will go higher than AB2. Okay, and we have been given pure A's melting point, which is about 940 degrees centigrade. So we'll keep it there. And pure B is 830 degrees centigrade, which will be kept somewhere here, 830 degrees centigrade. Okay, and what else? We have maximum solid solubility given, and we have the temperature of eutectic. So first eutectic is 700, then 730, and 755. So 700 occurs somewhere here. We have increasing order of melting points, right? So we will be having 3 eutectics, but that we know that this melting point is given. So this melting point of AB is 780 degrees centigrade, right? This is 780, and the melting point of AB2 is 755 degrees centigrade. Now that will help us to know where the eutectic points are. So the first 700 degree eutectic will be lower than this point, right? So this eutectic will lie somewhere here. Okay. So this is the eutectic at about 700 degrees centigrade, and 755 lies so third eutectic is 755 degrees, right? So 755 is here and 730. Okay. So 755 lies here, right? And the third eutectic 730 will be somewhere between 700 and 755. So 755 is here, 700 is here. So it should be and so naturally we have been said that there is no solid solubility. So no solubility of B in A. So that's the reason we have no dimple. So it will be a pure vertical line here. And this is the third eutectic is already given to us. Third eutectic, so this is 730 degrees centigrade. And third eutectic is 755, which is mentioned, which is equal to the melting temperature. Right, so this will be going this way. And the composition of the eutectics, we have to mark it. This is 7%. Okay. else. So we have been told the maximum solubility of A in B is 12.8%. So we know that this melting point is here, right? And the maximum solubility is 12.8% of A, that is 88.8% of B. That means, by the way, this starts with 600 degrees, right? And this is 88% of B, and at about 600 degrees centigrade it reduces to 92. Okay, about 600 degree, so 600 degrees here, so this reduces to 92. So instead of drawing it close to 100, it should go something like this. This is 92, and at 600 degrees centigrade the salt was to touch 92. So yeah, so this is the hypothetical phase diagram that was asked. So it's easy to fill out the phase now. So this is pure A, so this is A plus liquid, and liquid denoted as L. This is AB here, and this is liquid, so L plus AB, and this is A plus AB in this phase field. Then we have AB plus AB2, and then we have AB2 plus beta liquid. So this is liquid plus beta, and liquid plus AB2. We have liquid plus AB2. So this phase field is same as this field. This phase field is same as this phase field, and we have liquid plus AB. And correspondingly, this phase field is same as this phase field. Okay, so this is the eutectic, multiple eutectic phase diagram question was asking us. Okay, so now we'll move on and see another phase question. So next question asks that we have a phase diagram, this one. Yep. So we have a phase diagram of again a hypothetical phase diagram that is shown here, and the first question asked is, are there any intermetallics present? So if so, identify them and determine whether they are stoichiometric or non-stoichiometric. So first of all, between A and B, we should see that if there is any vertical compounds, line compounds. We don't see any line compounds like we have seen in the previous AB and AB2 case, but rather we see some compound that is forming the theta phase, but this theta phase then has a extended solubility in both A and B. That's the reason why instead of forming a simple line, it is has it is widened to a region like this. So yes, there is an intermediate compound theta, and this theta is a non-stoichiometric intermetallic compound. Okay. Second question asks us, identify the solid solution present in the system. Okay, it's pretty easy because we have solid solution of B in A, which is represented by this field here. The solid solution of B in A, right? So we have alpha, and then we have this phase here, solid solution of A in B, the eta, have gamma. Then we have gamma phase, right? We have a gamma phase. Again, this is solid solution of A and B, and then we have beta space. This is also A and B. So you see, for A and B we have 3 possible solid solutions depending on the temperature, right? And for A in B, for B in A we have only one, that is alpha, which is ranging throughout the entire temperature range. Okay. And right. So the third question asks, so the second part asks, is material A or B allotropic? So material B is allotropic because it is existing, as I said, in 3 different, because it is existing in different solid solutions. Therefore, B is allotropic in nature because they have different allotropes, different forms for a given formula. Right? So B is allotropic in nature, not A. Okay, the next question asks us, identify the phase reactions by writing down the temperature. Okay, so writing down the phase reaction by writing down the temperature, the reaction in equation form, and composition of each of the phases. Okay, so again it requires a bit of slide. So at about 1100 degrees centigrade, we will see at 1100 degrees centigrade what reaction we have. We have a peritectic reaction, right? Because there is a gamma plus liquid to gamma plus beta. So we have a gamma plus liquid. So if we take this peritectic point, gamma plus liquid transforms to pure beta. Beta upon cooling and upon heating, it transfers this way. This is a peritectic point. Okay, so it's easy to again get the compositions. You just have to see the tie line intersections with the solidus and liquidus. For this question, I'm not going to do that because we have already done multiple times in this lecture today. For at 900 degrees centigrade, we have this eutectic point in which L1 transforms to alpha plus So since it's not a complete solid transition, so we don't have an actual solid below 900 degrees centigrade. We have alpha plus liquid, so it is called a monotectic, not eutectic. Monotectic point. And at 680 degrees centigrade, let's see, 680 degrees centigrade, which is closer to 700 here. We have a pure eutectic form because we have L2 to if you see this, and if you see this, we have liquid to complete solid transition. So L2 transfers to alpha plus beta, right? This is eutectic point. And at 600 degrees centigrade, again 600 degrees centigrade is here, we have a, because we have this here. So here alpha plus beta, it transforms to theta, which is a again a solid, but it's like a solid to solid phase transition. So but the composition of alpha and beta is changing after you heat or cool it, right? That's the reason why it's not eutectoid, rather it's peritectoid. Right? And finally at 300 degrees centigrade, you can see. So here beta plus eta transforms to theta plus eta. So it's a solid to solid transition, but here we are pretty much, this diagram looks like eutectic point, although there's liquid here, so it's a eutectoid point, not eutectic, rather eutectoid. So we have beta. So this is a complete beta phase. Beta plus eta is this one, so this is completely beta, as is mentioned here. So beta to theta plus eta. And this is called eutectoid point. Okay. Right. So we have been given, next question, we have been given an aluminum lithium phase diagram. Okay. So, and we are asked like whether there are any intermetallic compounds, like we have seen in the previous questions. Whether do we have intermetallic compounds? So yes, we can see that there is a beta here, and we have a gamma phase here, right? But beta is like having some solid solution tolerance with our aluminum and lithium. Gamma has no, it's a solid solution tolerance, it's a line compound, right? So yes, we do have them. So beta is now stoichiometric. And determine the formula for each compound. Okay. So for beta we have it centered about 21. It's centered at around 21 weight percentage of lithium. So atomic percent of lithium, because weight percent will not give us the stoichiometric formula, or rather the formula. So chemical formula is given by the atomic percent. So atomic percent of lithium is given by, so 21, assume 21 grams of it in 100 gram of alloy. 21 grams divided by the molar mass of lithium is 6.94 gram per mole. So this will give me the number of moles of lithium divided by what is coexisting in the entire mixture. So this is 21 gram, 6.94 plus 79 remaining, and in aluminum. So aluminum atomic weight is 26.9. So that will give us approximately 50%. So this is atomic percent lithium. Okay. So this will give us a formula of AlLi, 50-50, right? So second, we have a compound that's gamma, which is stoichiometric. Stoichiometric in nature. So the gamma, we'll see the gamma exists just about 34% of lithium. So we take the atomic percent of lithium here. And that is given by 34 grams, assuming divided by 6.94 gram per mole. So number of moles of lithium by total number of moles. That should give me 66.7% lithium. Now if I just convert into fraction, 66.7 gives us 2/3, right? So if I have lithium 2/3 and let's say aluminum is unity, and if I multiply 3, I will have Al3. So if I just if I have 2/3 of lithium, so if I have let's say aluminum of 1, then I'll be having lithium as 2, because then lithium, for 2 atoms of lithium, we have total 3 atoms of the entire alloy, so 2/3, right? So it is Al2. This is the formula of the stoichiometric gamma compound. Okay. So the second question asks us identify the phase reactions. So identify the 3 phase reactions by writing down the temperature. So we can see first there is a eutectic point, and second there is a peritectic point. This is a peritectic point here, and third we have another eutectic and very close to here, right? So just write them down whatever we see. So at 600 degrees centigrade, we have a eutectic point, right? So liquid transforms to alpha plus beta. So compositions again can be worked out by just taking the intersections with solidus and liquidus, and it's at about 500 degrees centigrade, just close to 500 degrees centigrade, we have a peritectic point wherein we have beta plus liquid transforming to gamma. And as you can see, upon heating gamma, we have a formation of beta plus liquid, but the liquid that is first forming has a composition of this, the beta has composition of this. That tells us that the liquid that we are forming has a composition that is different from the parent compound, and that's a peritectic point. Okay, and this is about 500 degrees centigrade. Third question was the third invariant reaction is at about 170 degrees centigrade, as you have seen. Much lower temperatures, lower than 200 degrees centigrade, we have this eutectic much reaction that is closer to the pure lithium phase. And here liquid transforms to gamma. So this is the gamma plus alpha. So in this eutectic temperature, we have a transition from gamma plus alpha to liquid, or rather the opposite way, because we are cooling it down, right? It is this way, consistent with our terminology. So liquid upon cooling down will give us gamma plus alpha. Okay, and this is again eutectic point. Okay, so this is done. The next question is pretty similar to this. So we have at about 74 weight percentage of zinc and 26 weight percentage of copper, cite the phases present under following temperatures. So it's pretty easy to see. So at 74 weight percent, we'll be lying somewhere in this region. So this is 70, so 74 is between 7. So here we have This is where we are. Okay, and yeah, so at 850 degrees centigrade we are completely in liquid. At 750 degrees centigrade, so we have this gamma and liquid phase is present, right? At 680 degrees centigrade we have delta plus liquid phase, right? That's over here. At 600 degrees centigrade we're completely in the delta phase, right? Over here. So we're completely in the delta phase. And at 500 degrees centigrade we are the gamma plus epsilon phase. Epsilon phase is there. And the composition again can be formed by the intersections. I'm not going to do that, so it is straightforward. Okay, so I think I'll stop with this. So in this lecture we have seen the different equilibrium concentrations of the alloys when it is cooled slowly, and then like what happens if you are not cooling it slowly. So we have non-equilibrium concentration, when non-equilibrium deposition of the phases such that the concentrations are not corresponding to equilibrium concentration. That's the reason we have a shift in the solidus and liquidus lines. And then we went about solving few numericals that require the knowledge of the phase formation. Specifically, we saw for questions relating to the calculation of pro-eutectic alpha and the hyper-eutectic and hyper-eutectic regions. So next week we'll be seeing numericals based on a more practical example of iron-carbon steel diagram. So iron-carbon diagram is the most popular diagram in metallurgy, wherein we have very low percentage, or we operate in the very low percentage of carbon. So we see very close towards the very close region, 100% iron region. We have different steel phases, and that is what is of relevance in engineering. So thank you so much. I hope to see you next week. Thank you.